Now I'd like to introduce our webinar topic for today and our speakers. Our webinar today is Mapping Road Salt Storage Facilities in Vermont's Lake Champlain Basin, an analysis of potential drinking water impacts in vulnerable communities. So our presenters can get their sharing going. They are Stephanie Hurley and Dana Allen. Stephanie Hurley is an associate professor of ecological landscape design in the Department of Plant and Soil Science at the University of Vermont. Her research includes watershed and stormwater management, ecological design, urban agroecology, landscape architecture, and planning for equitable cities. Dana Allen is principal of Fluid State Consulting, a Waterbury, Vermont-based consulting firm that focuses on improving water quality using drone mapping, innovative online GIS, efficient stormwater runoff modeling and design, and water quality education and outreach. And with that, I will pass it over to our presenters.
All right, thank you so much. I'm going to be kicking this off, so let me just get the share going. Stop two. There we go. All right. Well, thank you for that great introduction. Our research today, as sort of already summarized, is about the potential drinking water impacts from road salt storage facilities in the Lake Champlain Basin. And so Dr. Hurley and I did this project over the course of 2023. And first of all, we'd like to acknowledge, hold on, there we go. Some of our funding for this was the USGS under the Vermont Water Resources and Lake Studies Center. So they allowed us to do this research. We also had a lot of help in creating this final product, from doing the work to a lot of good advice. And so would really like to recognize our research assistant, Oscar. Oscar was incredibly diligent. Oscar is an undergrad at UVM. A lot of early morning phone calls for Oscar in developing this database, a lot of great follow-up. And if you're looking to hire someone to do good quality work who's going to be consistent and persistent, Oscar is your guy. Please don't take him away from me for certain projects. I still need him. Also like to recognize a couple of our important collaborators in this, doctors Chris Stepanuk and Cheryl Morse at UVM. They gave us a lot of good advice. We wrote many different proposals, and their insight helped to develop this one, as well as Dr. Rebecca Tharp, who's a great colleague and collaborator with Just Water Consulting. Scylla Larson gave us a lot of really great insight and help in her position formerly at DOH, Department of Health. Diana Butler and Brad Roy rather, at Vermont Rural Water Association were also really helpful in developing the scope for this project. DG at VTrans, DG did a lot of data share, chatted with us frequently, and offered some insight on the final report that was really helpful. And also the Vermont Environmental Disparity Index, which if you're not familiar with this, you'll get a little bit more familiar with it today, is a really interesting and novel product that was developed at UVM by Drs. Ching Ren, Bindu Panikar, and Jillian Galford. It's a great resource. It's online. I love it because it's GIS and it's online interactive, and we use their results in our study to give us a little bit of an idea of communities potentially at risk. So with that, I'd like to give you a little bit of background on this. Without going into too much depth, the use of de-icing materials, in particular road salt, in Vermont has increased in recent decades, where we have a lot of roads, we have a lot of freeze-thaw events. Some people say we have the most freeze-thaw events in the country. And so as a result, our road salt use has increased on our, highways and feeder roads. And while it's a great thing for safety, chemicals like sodium chloride can pose a risk not only to surface waters like streams and lakes and wetlands, but they're also potential risks to our drinking water supply. And in fact, 40% of drinking water in Vermont comes from private wells. And one of the things that we're a little bit, that is potentially of concern is that the quality of the water in those wells is not regulated by state or federal agencies. And monitoring is the sole responsibility of the private owner. And so there may not be a high level of scrutiny through these or for this water. And one of the issues there is that higher levels of chlorides in this water can actually liberate certain chemicals within types of plumbing, in particular lead. It'll also liberate copper and radium, and this has been shown in other studies. So while the road salt itself might not be of particular concern, what it can potentially do, especially in older plumbing, is of concern. And so this is something that we think deserves attention, and hopefully our study leads into a potential way to investigate that more closely. And this is sort of building on studies within the Lake Champlain Basin in New York, which has shown that these concentrations of sodium can be harmful to human health in residential drinking wells adjacent to salted roadways and salt storage sites. And also that chlorides in domestic well water can promote corrosion in pipes, so liberating copper and lead. So this has been seen in the Lake Champlain Basin and in our neighbors in New York. So what is different about our study? I think this is really the meat and potatoes of this, is that salt pollution is typically associated with roads in the winter, which are a distributed and ephemeral source of this. Imagine you're spreading road salt on a road. It happens in the wintertime. Some is still residual along the side of the road, but for the most part, it's well distributed and it's only part of the year. But storage locations for this material represent a potential localized perennial source of pollution. So these are facilities that are there year round, that may have risk factors associated with them. And prior to this study, there was no mapped database of de-icing material storage locations anywhere in Vermont. I checked, I tried to find it for other research, it didn't exist. And so essentially that was one of the inspirations for this. We didn't have the information we needed to build on and to create other studies. So that's what we did within the Lake Champlain Basin, is created this new database. So the study goals essentially were to survey the municipalities in the LCB, to map their de-icing material storage facilities, but not just for location, also for material type, and maybe more importantly, storage methods. Are they covered? Are they not covered? What are they covered with? Are they on an impervious pad or not? Because if we're talking about groundwater, we have to talk about exclusion from groundwater. How long have they been stored there? If it's a newer site, maybe there's no residual risk. If it's been there for 10 plus years, potentially that is a higher risk. So we wanted some attributes as well. And then we wanted to analyze those facility locations with respect to distance from private wells and public water sources. We wanted to make an estimate of down gradients, hydraulic down gradients. We'll get into that in a little bit, but that's a relatively complex thing. We also wanted to look at school water sources, because if we're thinking about this, like children are at potentially higher risk for some of these factors. So could we tease out any details there? And then we also wanted to get at, are these facilities located closer to vulnerable communities? Is that something that we can actually pull out of the data that we have? And that is where the environmental disparity index came in handy for us, in trying to tease out some of those details. So basically in today's study, we already talked about the background of the study goals. We're going to go through the methods that we used to map municipal and VTrans de-icing material storage facilities. We're going to talk about how we selected the wells and the water sources that are quote unquote in proximity, how we compared it to the EDI, and then how we determined school proximity to some of these de-icing material facilities and their wells. And so we're going to talk about the locations and descriptions of those facilities, the wells and the water sources down gradient, the results that we found with the EDI, as well as school proximity, and then briefly conclusions, but maybe more importantly, the next steps as well, because this is the first step in hopefully what will be a multi-step process. So first of all, we need to develop this database because we have to have something to analyze. And so for the municipal facilities, this is where Oscar's diligence and persistence paid off. We sent out an online survey via email, but really what it came down to for the most part was calling towns, talking to road foremen, public works people, that sort of thing. And so all of our facility locations are based on town official responses. We've not field verified these, they're just what they told us. We did try to use satellite imagery and place points where they told us the facility was, but we haven't been there to definitively say yes or no. DG came in from VTrans and they had already mapped out all of their facilities, so they were able to give us that data directly. And then what we did is we gathered this data for the munis in Fulcrum, which is a third-party database, geospatial database collection app. And then we exported and collated in ArcGIS. And then we actually serve this data on the Vermont Open Geodata portal. So if you look for municipal de-icing storage facilities on the Geodata portal, you can get access to our data as well as metadata describing what it is. And the VTrans data is available directly from them. They hold that data. And so DG would be your contact for that data if you're interested in seeing those locations. So the wells and the water sources, these mapping methods, these are both publicly available layers on the Open Geodata portal. Again, can't say enough about the Open Geodata portal. We're so lucky in Vermont to have that. But the private wells are something that is held and developed by Vermont Agency of Natural Resources, and it's their water supply data composite and their water well advisory committee data. And this is water well data that's been delivered through the water well driller licensing rule since 1966. I think that's important to keep in mind. We've been collecting these reports since 1966. Data quality may vary. So spatial inaccuracies or incomplete data are definitely part of this data set, but it's the best we've got. We've got 110,000 reports in there. It's important to keep in mind that it's not all drinking water wells necessarily. Monitoring wells and geothermal wells are included in there, as well as wells that have been closed. And so for our purposes, we basically looked at anything that's in there. And so this could be for single family homes, public buildings, subdivisions, or public water supplies. So again, there's a lot of nuance in this data. We just looked at the locations themselves in determining proximity and down gradients. For the public water sources, we just use the Vermont DEC's state drinking water database, which includes active and inactive public, which are community, non-transient, non-community, and transient, non-community water sources. These can be wells. They can also be intakes or springs. So lakes may be included in this. Think about like the Lake Champlain Basin. Many communities get their water from Lake Champlain itself. Those intakes would be part of this database. So this is sort of a wider database in a way, but it generally serves more public-facing entities. So that's the difference between private wells and these public water sources. All right, so this is interesting. We wanted to figure out if we could determine, it's easy enough to figure out proximity, and we'll go into those methods a little bit. But can we figure out hydraulic down gradients? Can we figure out when rain hits the surface, what it does underground? Is there an easy proxy for that? And the funding for this project didn't really allow us to do any specific groundwater modeling or sampling. So we made a bunch of assumptions and we have a bunch of caveats. And we thought that this was a pretty good way of getting at the first cut of what might be down gradient. But we basically used topographic gradient as a surrogate for hydraulic gradient. Now, is that always true? Well, the next slide, which has really high-tech animations, will kind of illustrate that over here, if we have water hitting the surface of the ground and all things being equal, it'll generally follow the slope, the topographic slope of the ground. And that's just sort of a general assumption. So that's topo equals hydraulic. So anything that's downhill of that rainwater, it is going to be downhill of the groundwater. Now, what happens if we get into a situation where when the rain hits the surface, it then hits a bedrock fracture, which sends it in an entirely different direction than topographic gradient? We didn't take that into account in this. We don't necessarily have the data to do that for a statewide study like this, or nearly statewide, basin-wide study like this. So it's topographic gradient is not always going to equal hydraulic gradient in areas of things like bedrock fracture. So that's one instance in which topo doesn't equal hydraulic. Another instance is this, where we have the ground surface, we have a surface flow, which is again going to follow that topographic gradient, and then we have our groundwater lens or groundwater table down below. And in this instance, we have this facility that's, fairly low in elevation. And we have a well that's up above it. So this well is topographically uphill of that facility. So you could say, okay, it's topographically uphill of the facility. There's really no risk because it's uphill. There's not going to be any groundwater contamination from that. But that's not necessarily true because that's not how wells and groundwater work. You could have a well that's topographically uphill of a facility that then actually taps into the groundwater that is hydraulically downhill of that facility or down gradient. So these are the limitations of this method. They're not perfect. They are a good first cut, and they give us a way to look at, a lot of different points and get an idea of, well, how many wells or how many private or public water sources are potentially downhill of these facilities or hydraulically down gradient of these facilities. But it's not predictive in the way that true groundwater modeling and testing would be. So that's a big caveat with this data, and we just wanted to get that out there first in an attempt to make sure that everyone kind of understands the limitations. So the other thing that we did here, this is basically an extension of this method, is if we're just saying, okay, topographic gradient kind of stands in as a proxy for hydraulic gradient. So we're able to assign the wells and the water sources an elevation using the LiDAR DEM. Again, we have a great statewide LiDAR DTM, digital terrain model, so bare earth surface. And we were also able to assign each facility an elevation. So then we can pretty well figure out like what's above and what's below, at least based on ground surface. And then we also used 5 selection distances of 30, 60, 100, 200, and 300 meters as sort of our selection method for proximity. And we'll explain a little bit why we chose those. We also use the National Hydrography Dataset high resolution catchments for drainage area boundaries. These are actually like really fine scale drainage area boundaries for water. So they show you where surface water flows. Again, we're just using topographic gradient as a proxy for hydraulic gradient. We're saying, okay, if these fine scale catchments show where surface water goes, that could be a proxy for where groundwater flows. So that was our other sort of selection method. So buffers and catchments, and you'll hear a lot about this in our data. Why did we choose those distances? Well, we chose them based on the literature. 30 meters or about 100 feet. This was shown to have an impact. Basically like groundwater impacts were seen within 30 meters of roads in a 1982 study from Heindel, a Vermont-based study actually. And we also saw that same data popping up from a study in 2018 in New York. They were finding that within 30 meters, there was a significant impact from roadways. So again, we're not talking about roads, we're talking about salt storage facilities, but we wanted to see what we had within 30 meters. 60 meters we use as a proxy for the 200-foot minimum distance as specified in the Vermont wellhead protection rules. Again, that's kind of a blunt 200-meter radius circle. It's not really a refined groundwater model, but again, it gives us a first cut. And then we also used 100-meter, 100, 200, and 300 meters to broaden our search radius, because honestly, we weren't getting a lot of results within 30 and 60 meters. And so we just broadened our search radius. And so that gave us something that looks a little bit like this. And so you can see we've got our distances here. So 30, 60, 100, 200, 300. And then these black lines here are the catchments. Those are those NHD high resolution catchments. So the surface drainage essentially. And in the center of all this, we've got a facility. This is a covered municipal facility. And then all of our wells are around it. And again, with that assigning of elevation data to all of these wells and facilities, we can see that in this case, this well is actually higher than the facility, whereas this well is lower. So making our assumptions of topo equals hydraulic gradient, this lower well might be at higher risk versus this one, which is not. And then all of these have inset maps. You can see these are, the catchments here, those high resolution catchments. We capture a few more wells. And again, These green ones here are generally higher than the facility topographically, whereas some of these little orange ones down there are lower. And so that's how our data breaks down. So those are the maps that we produced. Getting into the Vermont EDI, this summarizes social vulnerability, and it looks at health risk factors and environmental risk factors at the census block level. And that's important to keep in mind, census block level. And so the EDI is basically environmental exposure multiplied by health risk times 0.5, plus social vulnerability times 0.5. And you can go online. Again, this resource is huge. It's online. It's interactive. And you can see how they developed this environmental disparity index. It's a great resource. So we won't go into all of that here, just to say that we use the EDI to compare with our data. I mentioned that it's at the census block level, and that's important because that's not always equal to town boundaries, especially in places like Vermont, where we kind of aggregate some of these towns into census blocks. So we essentially just join the EDI values with our town boundaries. And then we're able to select towns with map facilities and the associated EDI. We also ran a near function with each well and water source. So it assigned a distance in meters to the nearest facility. And what we wanted to do with that is basically see if there was a relationship where wells that were near to facilities, if they fell within communities with a higher or lower EDI. And so that's why we ran that near function. We'll get into that a little bit in the results. We also averaged this distance by municipality and compared that with Vermont EDI to determine if there's like any linear relationship between the average distance and the EDI values. So then we wanted to look at determination of school proximity, or really rather school well proximity to deicing material storage facility. We did our best to pick out the relevant data from the private wells and the water sources database, and essentially just keyworded where the owner's or purchaser's last name contains school, or where the water source system name contains school. And so that was how we derived the water sources for those locations. And we'll talk a little bit about that in the next steps, but just keep in mind that there's no mapped database of school wells or water sources that we were able to leverage. It's just leveraging those same two databases and picking out what we could pick out. So from all this, we were able to create essentially two overarching maps, one of the Vermont municipal facilities within the Lake Champlain Basin, and to signal whether they were covered or uncovered. And then a similar product for VTrans facilities. We'll talk about the difference, but you can see that these are the overarching maps that we were able to create of those two different data sets. Within that, so for the municipal facilities results, we essentially picked out 126 muni boundaries in the Lake Champlain Basin. Of that, there were a couple of GORs, so they don't really have a formal administrative structure. One, St. George, had no road department. They only have 2 miles of road, so they rely on a public or a private contractor. A couple of towns share facilities. One town chose not to participate, and 2 towns, despite repeated contacts, didn't respond back to us. Again, Oscar, thank you for your diligence. Sometimes people don't answer the phone. So basically, at the end of the day, we have 122 facility locations over 118 towns. A couple of towns have 2 facilities. 43 towns store multiple materials, so things like salt and sand, as well as road salt. And so that basically gives us 170 individual material piles throughout the basin. 36 of these, or about 21%, within 29 towns are uncovered. But the majority of those, at least from what we were told, are salt and sand piles, or 8 of them, they say, are only sand or sand and gravel piles. So in terms of materials, this kind of makes sense. If you leave salt out in the rain all the time, you're not going to have salt after a certain period of time. And so there's still, it's not a non-zero risk with salt and sand piles because they do contain some level of road salt, basically to keep the pile from freezing, so you can actually handle the material. But the majority of piles in Vermont do seem to be covered. So that's a good thing. One material pile was initially listed as uncovered, but actually it's a magnesium chloride store in Milton and is actually covered. We checked with them. So the results are a little bit off there, but we figured it out. For VTrans, they have 124 facilities across 63 towns. This is both in the Lake Champlain Basin and without. The specific attributes for all of these wasn't provided. So coverage method, pad type, storage duration, material type. But in conversation with VTrans, they state that all of these piles are covered and on impervious pads. So, basically best practice as far as that goes. What are the material types we're looking at? Most are sodium chloride, road salt. 24 are salt and sand, or at least 24 piles are salt and sand. Not a lot of potassium chloride, one of those. A few magnesium chloride. Potassium chloride and magnesium chloride are often used at different temperature gradients than road salt, so not as common. And other materials include calcium chloride, which is usually liquid, so that's a brining solution essentially. So that's going to be stored in tanks, so by definition, kind of covered. We found that for the most part, these sites have been active for 10 plus years. 151 sites, I should say sites, not towns, have been there for 10 plus years. Coverage method is typically structures. 127 piles are covered by structure. 7 were covered with an impermeable membrane, so a tarp essentially. Most are on pads. Pad type does vary, but at least most of them are on these pads. So it's preventing material for, if there is some level of water intrusion from getting into groundwater. 45 are not on pads. Most pad material is either asphalt or concrete, or maybe a mix of the two. There was some compacted earth, a couple were concrete and asphalt. One was listed as pine boards, which we chose to look at as impervious, but that's a bit debatable. Asphalt and dirt, depending on level of compaction, could be effective, and some are unknown just because it's covered and they don't know what's under there. So for our wells and our selection methods, so remember we had those distances and we had those catchments. We found 1,600 basically wells within 300 meters or within the catchment, and 44% of those were topographically down gradient of the nearest facility. 1,076 of those were in a catchment, and 63% of those were topographically down gradient in the facility. And we basically tease that data out because within those catchments, we feel like that's potentially a higher risk just because of the topographic gradient. Basically, all surface water is running down to those down gradient wells, so potentially deserve a higher level of scrutiny. Again, with the caveats that hydraulic gradients isn't always equal to topographic gradient. We only found 15 wells within 30 meters of facilities, so that's in some ways encouraging. Again, 589 wells were within 300 meters. So again, remember, we kind of broadened our search distances to 100, 200, 300 meters. So we're not seeing a ton of wells within 30 or 60 meters of these facilities. That said, there are still 46 within, a couple hundred feet of these facilities. And if we're prioritizing wells for testing or additional scrutiny, those might be the 46 to start looking at. So at least this gives us a first cut. For public water sources, we had 51 public water sources within 300 meters or within an NHD catchment, and 63% of those were down gradient of the nearest facility. And so again, not a ton of sources, but we do have a bunch that could potentially be ripe for additional scrutiny. And so now I'm going to turn it over to Stephanie, who's going to go through some of our additional results in terms of the maps that we created, as well as the EDI data.
Thanks, Dana. Thanks everyone for being here. And thanks, Dana, for the setup to the results in terms of the maps we made. If you could just click to that heading goes away. Mm-hmm. So Dana already reviewed how to interpret the maps, but I'm just going to go over a little bit again, because this is one of the products. In addition to the database, we did create one of these kind of bullseye style maps for each town. And so that I will show you at the end of the presentation how to find those maps. But looking at this particular example here, as Dana pointed out before, now that you kind of understand what's covered, what's not covered, covered meaning having some kind of roof or membrane on top, and not covered lacking those. You can see some of in this map example here, you've got multiple drainage area boundaries, those catchments Dana referred to, as well as the topographically higher than facility and topographically lower than facility. This is on a ridge, so it's kind of surprising, like which way is topographically above or below. And so these legends are shared for all the maps. It's the first page of our map appendix, and the legend is going to include the same information regardless of whether, for example, this site has no VTrans facility, but the VTrans legend is still there. Next. Go ahead. This next example, this series in Aalborg on the left. Dana, wait and click when I say. Okay, I want to walk through at a different pace. Aalborg has an uncovered pile. It's that orange triangle in the middle, but you can see that there's actually no wells within even the 300-meter band around that, and multiple catchments in a relatively flat area. Next. Looking at Chittenden, there's a smaller catchment area that the entire catchment pretty much is within that 300-meter band. So the distance rings are relevant as well within that catchment. And there's a mix of some above and some below, but not too many in this area are meeting all those criteria. And there's a couple though within that 60 meters. This is one of those areas where the 60-meter, AKA Vermont's wellhead protection 200 feet rule would actually potentially flag a couple of these sites as close a salt pile close to the wells. Next. And this one I just wanted to show as one of the examples where it gets complicated, because we have in the same map 2 VTrans storage facilities as well as a covered municipal storage facility. And so the rings start to overlap and get, more dense in certain areas. And so all of this has to be taken into account when you think about site context. So these are just 3 examples, but these maps, I think 118 total for the project sites. Next. Okay, so again, as Dana really described so well, we very much were thinking about, so who might be the most vulnerable? Is there an instance where, if we're going to do water testing, we want to make sure to consider vulnerable populations before others? And so in the environmental disparity index developed for Vermont that's cited here, the higher the number and the darker the color on the map equates to the higher environmental justice, environmental health risk for those communities. And again, it's at the census scale, census block scale, as opposed to municipal scale. So we worked around that a little bit. But so one of the maps in our report shows all the VTrans locations, the municipal locations, and how they fall within the relative EDI score category. Next. So this was a way where every town every municipality that was in our study is placed along the x-axis across the bottom here. We didn't have room to name all the 100+ towns. But the furthest to the left is the highest environmental disparity score. So sort of the worse off towns from a community vulnerability standpoint. There are more vulnerable people in the population of that municipality based on the map, and the lowest vulnerability on the right. We plotted that with these green dots to represent the distance in meters between wells and de-icing facilities. So you can kind of see here, there's not much of a trend. And we also show the significance or lack thereof there was no sort of linear relationship where perhaps we would say more vulnerable communities live in places where salt storage is near their wells. So we did not find a trend there. Next. But this is the same figure in the upper left corner, just as a reminder. We also thought in table 1 a little bit about is this representative of the whole state? And interestingly, these averages, medians, and standard deviations show that the Lake Champlain Basin municipalities are actually very similar to if we had done this calculation statewide. So representative of all of Vermont, you can see in the Lake Champlain Basin, because it has like the more urban, the more rural, there's disadvantages in populations in both of those categories. So we did sort of determine that the municipalities within the Lake Champlain Basin represent the overall statewide trends in terms of EDI value or disparity index. And then in the second table, we looked at maybe there is a trend, and you can see from the R squared and P values, we did not find a trend, but we did want to consider maybe there would be a relationship at like the shorter distance, the mid distance, or the longer distance between facilities and well locations. So Dana described in the methods how all wells in all municipalities were run as a, quote, near function. And that near function helped us kind of determine these approximately in thirds distances. And again, there was not a relationship where you could say vulnerability as measured by the environmental disparity index correlated with closer or further distances from wells statewide in the municipalities that we looked at. Next. So again, though, we wanted to just dive a little bit deeper, and we put the top 25 highest EDI scores into a figure here. And so you do see the towns named. And so again, the highest score means the higher likelihood of vulnerability due to environmental disparity, environmental justice issues, and health issues. And so again, though, we did not find a relationship with what you see in those green dots of distance between people's wells and these de-icing material storage facilities. They're all sort of lined up as the 25 most vulnerable towns or that have the most vulnerable populations within towns, but there was not a relationship there either. So, however, even though we didn't identify a statistical relationship, we still think that using the environmental disparity index is a valuable lens where we can look at prioritizing towns. So if a town is high on this index, those are towns where if there is going to be well water testing or public water source testing that potentially connect to the infrastructure for vulnerable people, it makes a lot of sense to start with those towns. Again, this is census block scale data, and so we had to ascribe sometimes multiple towns into the same census block, so that's an important caveat. But in the meantime, this index confirms that there are proportionally more individuals in some towns than others that are likely to suffer from other environmental factors, and it, to me, makes a logical prioritization scheme for any future water testing. Next. Okay, so schools, another, potentially vulnerable population based on school children's ages and so forth. We found there were 54 private wells in Lake Champlain Basin potentially associated with schools, and 2 in that within 30 meters of a school's well or a possible school's well. And I can talk about these potentially possible caveats within that 30 meter to 300 meter distance, or within the catchment. So there's only a couple schools where it's really close. They're not on this slide, but one of them is actually Yestermorrow, which is more for adult education. It's Yestermorrow School, so it showed up in our data, which is 55 meters between a salt storage facility and a well. And then another one is in Plainfield, in Twinfield School District, and it's within the same catchment, but 1,500 meters away and 100 meters topographically above. So we're kind of less concerned about that particular example. There are 12 public water sources in the Lake Champlain Basin potentially associated with schools. 2 of those are duplicate records. So 10 total that were within either the same catchment or the 30 to 300 meter buffer distances that we showed in some of our other maps. Next. This is another way to think about, this is just the public water sources, not the wells. And so a couple of things to note here. One is that Vermont law already requires water testing of childcare facilities and schools. And actually my school's results for lead testing for my kids' school, my children's school, just came in this week. So that was really good to see that they're lead-free in their drinking water. So this is kind of an active program that's ongoing. So we didn't put this list here to really scare anybody, but we did want to kind of make some notes. So you can see topographically below or above in that second column here. So there are 5 schools here. If you click, these 5 schools are below the de-icing facility topographically, either the schools or the well associated with the schools. So there can be some variation there. And then if you click again, you can see that this one actually is an uncovered facility that has both salt and sand. So Wolcott School, it maybe would be, because the facility is not covered, one I would think about testing the water there first. And then the next is Mount Holly School, where it's covered, but it's closer to the facility. It's 68 meters between the well and the facility in that distance, which is still, bigger than the wellhead protection limit of 60 meters. Next. Okay, so I'm going to go through some conclusions. I know we've thrown a lot of information at you, as well as quite a few caveats and contextualizations. So go right ahead to the next slide, Dana. We are happy that what we gained from and learned from this study includes the construction of this spatial database. It was not previously in existence. It's now publicly available. It is imperfect in that we haven't field verified things and so forth, but it is a database that didn't exist before of at least the Lake Champlain Basin portion of Vermont's salt and sand and other de-icing materials storage facilities. So that's there. We also started down the road of researching potential risks between private wells and public water sources and these storage facility locations. Other past research has focused more on surface waters and risk from roads. So we're kind of looking at a new possible but not determined relationship. But we started poking holes at the topic, and we'd like to keep going with it. And then we see this as a new opportunity to use the Vermont Environmental Disparity Index, looking at water quality. And we want to highlight how important that index has been and recommend other people use those resources as well. Next. So where do we go from here? As you could see from our earlier diagrams, the determination of what is hydraulically down gradient between surface water and groundwater varying in the way that water flows. So including more modeling would be really helpful along these lines, but we could also think about it at a larger spatial scale, modeling as well as monitoring. Applying the results to actually test water. So whether it's testing at people's kitchen sinks or some kind of citizen science effort, or some prioritization scheme related to applying the EDI, like I recommended before, that we have talked about, hey, if you're going to start a water sampling program for private wells, and again, Dana introduced this at the beginning, the private landowners are the ones responsible for water testing. It's not state or federally run. So if there is a scheme to work on more testing, starting in potentially more at-risk communities would be a good move. And then this database is for the Lake Champlain Basin municipalities, and then the VTrans facility statewide, but the other side of Lake Champlain Basin in New York, as well as the Quebec portion of the basins, could go, as well as the rest of Vermont, could all be places to further expand this database so we have more information about where these facilities are located. A few more ideas here. The schools, we talked about the methods we used to map them. There may be, instead of searching for the term school in the property owner names, a different way to use a mapped schools layer. I want to also note here that the city water schools, where there's water being piped from quite far away, sometimes from another town's boundary, a different water source, the proximity of those schools to a salt storage facility wouldn't matter if their water is coming from a place that is not in proximity to the storage facility. So there's some nuance there. Already we have, again, as I said before, water testing is mandated in schools in Vermont. Could we look at those results, though, for schools that are on well water with comparison to where the de-icing facilities are located? In municipalities, field verifying where these well locations are, as well as the facility locations. That was not something we actually looked at physically in the field. Verifying through testing and or modeling, or a combination of those, what the actual groundwater conditions and flows are. I learned a lot through this process and through some of our collaborators about like what is even considered a well, and sometimes things that are just sort of a dug well and very shallow are considered wells, but they're not necessarily in a well driller's database, but people are drinking that water. There's some things municipalities can do about that situation. Covering facilities that are not covered. That is a kind of low-hanging fruit thing, that if you have a town facility that doesn't have a membrane or roof on top or a pad underneath, adding those would be a beneficial move to reduce potential salt impacts. Again, the EDI has been great, and we want to see it used in other contexts, prioritization for water quality issues at all different types of land uses, whether it's, agriculture, drinking water, surface water. So I think that's a great place to expand for the research. And then we talked, go ahead, Dana, about ecosystem risks as something that people have studied in the context of chlorides pollution. And I still think there's a lot of potential to study whether not just the roads where the salt is distributed, but the facilities themselves and how they may be impacting streams, wetlands, and so forth, down gradient from them. All right, so this is where you can find the full report as well as the map appendix. So you can see in this screenshot here, the Vermont Water Center hosts a publications page. It's in that orange link. And if you scroll down to the 2023 publications, you'll see this reference. The underlined link opens a PDF of the main report. And the appendix with all the different maps is very sort of heavy. So if you want to open the appendix and screenshot the towns you care about, that might be in the legend for the map appendix. That might be the best move, rather than trying to store the whole appendix C, which is why they're kind of two separate documents. But if you want more information on the methods and more than we shared here today, it's in that report. And if you go ahead and click forward, you can also ask us questions in the future. So that's our contact information. We're very grateful for the funding for this project, and thanks. We'll take questions.